Hello, everyone. Thank you for having me at the Open Sky Symposium in Toulouse. And yes, my name is Maximilian Bień from Technische Universität Braunschweig, and I work at the Institute of Jet Propulsion and Turbomachinery. And I don't know how common it is to have engine people around in this community. Yes, but the work of Open Sky has been very useful in my research, and as a way of saying thank you, I want to present to you how I use it. So together with my student Philipp Lehmann and my professor Jens Friedrichs, I would like to present to you a generation of parametric climb trajectories considering operational factors for aircraft engine thrust extraction. And I want to go a bit further. The main introduction, it's that costs related to maintenance, repair and overhaul of aircraft engines or in general make up a great proportion of airline direct operating costs. And as we can see in the pie charts on the top left, we see about 10% of maintenance costs or 10% of direct operating costs are related to maintenance. And of these 10%, they split almost equally, where 50% are related to the aircraft engine. So costs over lifetime is a big thing. And maintenance actions have established several patterns over many decades of gas turbine operation. And it's also highly influenced by operational factors. So maintenance costs are affected by operation, and for conventional gas turbine systems or turbofan engines, there are correlations and metrics. As we can see in the bottom left in the chart, these are so-called severity curves, and by use of this, maintenance costs or shop visit rates, so maintenance metrics, can be converted from one operational factors to another. So we can see that the operational severity, it becomes more with shorter flights because of higher frequencies of takeoffs, and it becomes more the higher the takeoff thrust is. So thrust reduction is also always useful for prolonging life of the engine. But now aircraft propulsion systems are about to face a technological shift in mid or long term towards more hybrid or all-electric propulsion systems. And as we can see in the right chart, we have in blue the thrust demand of a climb profile with highest thrust at takeoff. And we can see in the severity factors, they are very much affected by thrust at takeoff. So peak thrust and the frequency of takeoff thrust demands makes up the most significant change in maintenance metrics. And now we can see on the right chart the relative thermal load along the climb profile for the engine, and the dotted or the solid line shows that peak thermal loads is at takeoff. And now if we consider hybrid electric aircraft engines, where the low pressure spool, where the fan is for generating the main proportion of the thrust, if it's electrically assisted for peak shaving at takeoff, we can see the dotted line where the takeoff thermal load is reduced, and such will the performance metrics of maintenance actions will probably change. So these severity curves, for example, they are not or in a different way applicable for aircraft engines, for hybrid electric aircraft engines. So this is where my research takes place, because there's a need for new models for the prediction of MRO for hybrid electric aircraft engines. So my motivation is to set up a model for predicting MRO actions or the sensitivity or how maintenance is influenced by the new propulsion systems. And there are the three main aspects. The first aspect is the propulsion system, the modeling of the propulsion system itself. This is my general scope, but not today. The other influences are operational factors, like ambient conditions or also aerosols because of fouling, erosion. And everything is done on a fleet average level, as are the severity curves. If we reconsider them, they are also averaged, generalized curves. So I want to stay in this scope. And on the right-hand side, you can see the scheme of my overall project. So it starts with flight connection, flight data, aircraft trajectory generation, which is the main aspect today, and then extracting the thrust profile, then doing the engine thermodynamic performance calculation. And by this, we know the operating point of the engine, and we can add on degradation models, and in the end, over degradation rate and so on, estimate maintenance costs. So the flight profile is very essential for the engine operation profile, and also for mapping environmental data, and in a third way, also for the operating strategy of hybrid electric propulsion systems. Because of the degree of hybridization, it's very sensitive to the operating stability of the gas turbine and changes with altitude and ambient pressure. And for doing so, for generating the aircraft trajectories, the OpenAP model from Junsi Sun was a very, very good foundation. Because it's parametric, it also delivers averaged trajectories. Also there is the aircraft-specific drag model, which is very useful for thrust extraction, and it's adjustable in Python, so we can adjust it to the specific needs we need. And so the aim is to customize the parameter set for the climb trajectory generation to consider operational factors. The climb trajectory in OpenAP is divided into segments. Yes, we can see on the right-hand side the red line. It starts with initial climb, precast climb, constant calibrated airspeed climb, Mach climb, and then ends in the cruise. And OpenAP also gives, from a broad analysis, the distribution of the parameter set, which defines the transition from one segment of the climb to another. And this is also drawn in the graphic, as we can see in the altitude and also in the vertical rate. And there are very diverse influences on the trajectory, which are physical aspects, flight mechanics, but also hard to simulate aspects of flight regulations, the human factor, and many on. And the assumption is that the operational factors, which are in the main course flight distance, which correlates to aircraft takeoff weight, and the ambient conditions at ground, air temperature, pressure, density, that these can be considered for more realistic climb trajectories. And here the transition altitudes and the vertical rates are considered. And the aim is to set up a database and to train a machine learning algorithm to predict these parameters. So the data acquisition, historical ADS-B data from A320 flights operated in North America over a period of 4 years have been downloaded from OpenSky Network. And then there's several steps for pre-processing, for assigning origin and destination airport of the trajectory, for checking for corrupted flights or only partial missing flights, so check the quality and the resolution, especially during climb, because there is where we want to estimate the parameters, but also origin and destination airport are very, very important to assign in a good quality because of the correlation of aircraft takeoff weight. Yes, and then the great circle distance is calculated. And we can see in the graph on the left, these are exemplary trajectories in North America. And then we have the atmospheric data, which is from the Copernicus Atmospheric Monitoring Service, which we have already seen here. And there a surface data set is used for ambient temperature, pressure, and the density is calculated. And also wind data is inserted to adjust for the true airspeed. And then the atmospheric data is mapped to the assigned origin airport and the timestamp of the ADS-B data. Yes, and so the data is further processed, as we can see in the right hand graphs. We can see the profiles of altitude. We want to retrieve the transition altitudes from the climb segments. And then the calibrated airspeed is calculated, which we can see in a second graph. And the segments are detected by the phases of constant calibrated airspeed, of constant Mach number. And when we can have the segments of the climb profile, we can calculate the average vertical rate of the segments. And in the end, we have a database of 3,000 flights. And then we trained a machine learning algorithm, of which we choose XGBoost, which is a gradient boosted ensemble random forest algorithm for supervised learning, and which in this task delivered or delivers good results also in other tasks with a relatively lower quantity of data already. And the hyperparameter optimization is performed by Latin hypercube sampling by minimizing the mean squared error, which is shown in the table. And yes, the machine learning algorithm is trained on this data. And here we can see the results in a parameter study. So on the left-hand side, we see the transition altitudes, which show that they have a great correlation with flight distance, which is why this graph is shown. The other parameters, the ambient conditions, are held constant at the median values of the overall database. And we can see quite reasonable results, especially, for example, for the cruise altitude, which is lower for short flights and then takes a steep increase, is constant, and for heavier aircraft, longer distance decreases. Yes, and you can also see the data distributions below, the distribution of the flight data. And you can see, yes, that the trends are visible, but they also have some singularities into the data, which are, yeah, not in a very smooth way, but also react to individual flights where you can see especially high concentrations of flight data. And on the right-hand side of the graph, there's also shown, again, the OpenAP distribution. And we can see that the data extracted and the altitudes which are predicted by the model are also in accordance to the OpenAP distributions. On the right-hand side, the same is shown for the vertical rates, but for ambient temperature. Yes, and so we see reasonable trends, and we see also no large deviations or unreasonable predictions, for example, in the areas right and left where we expanded a little bit the database. Then the influence on engine thrust is calculated. So we correlated, as I said, the takeoff weight of the aircraft engine from the flight distance. We used the OpenAP drag model and basic flight mechanics to extract the thrust needed of the aircraft to fly this trajectory. And on the top graph, you can see the default trajectory, the thrust profile, and in gray, you can see the deviation from the now generated trajectories with the model. And you can see the thrust deviates, and also the time the climb is performed also changes a lot. Then the average thrust demand per climb segment is calculated and shown as a box plot in the bottom diagram. And we can see that the median values, they correspond very well to the basic default trajectory. And the whiskers, they show the maximum and minimum deviation, which can take up to 20% near ground and then get less towards 10% with ongoing climb. And we can also see that the quartiles, they are concentrated very much around the median, but still have an influence of about plus minus 5% for the thrust of the engine. So the method shows, yes, a noticeable influence on the derived thrust and on the operating time, which is likely to have an influence in later degradation modeling and maintenance costs estimations. So to discuss the results, we have seen singularities in the trends, which could be handled by expanding the database, and also by maybe further hyperparameter optimization. Maybe it's an indication of overfitting, which these models used are quite prone to. Yes, and for machine learning algorithms, yes, the data is not equally distributed, and extrapolations, they have to be carefully investigated. So the model is only valid within the boundaries of the database, which is the North American airline. Yes, the database might be expanded to get better results, and the predictions have to be investigated carefully when exceeding the database. Other points are that the heuristic climb velocities for the climb profile, they are kept constant at the default values, because the climb velocities are much more difficult to retrieve from the ADS-B data because of the high influence of ambient conditions and wind. So before, to get the transition altitudes, the characteristic or the qualitative trend is of more interest because we detect segments of constant airspeeds, but the value itself to have a high high quality, it's much more difficult. And the overall process is different to OpenAP, so there might be an offset in the comparison of the data. And we have the uncertainty of the takeoff weight correlation. And also later on, when we want to model hybrid electric aircraft, there's a weight penalty because of the electric components. And so there should be a splitting possible between weight and distance. But it's difficult to get the takeoff weight right because of missing data. And it has to be noted, it's no representation of individual flights. It's a generalized method, and validation of thrust data might be necessary in future. So to conclude, a method is presented for adjusting the parameter space of the climb trajectory using the OpenAP model. And the climb can now be generated with respect to operational inputs. It's parametric and adjustable further also for other flight regulations or other future propulsion systems affecting the flight path in another way. And it's all based on open data and can be adapted for specific use cases or also be expanded maybe in a global way, which would be very interesting. So the precision of the model is in accordance with the global model, so averaged fleet averaged predictions. Yes, and the machine learning task seems appropriate for the task. So yeah, this is my presentation. I thank you very much for your attention, and I want to thank very much for the efforts of OpenSky and the models provided to make open data available for aviation research. Thank you.
Thank you, Maximilian. Now time for the questions.
You mentioned that you had to match origin and destination. Do you match it just by an airport database or by using maybe FAA flight plan data?
I used only an airport database, and I calculated from I built up a airline-specific airport database to not have all the global and small airports in the list. And then I calculated minimum distance to airport, and later I filtered, I think I showed it, I filtered the distance to airport to 8 kilometers for destination, 15 kilometers for destination airport.
Okay, maybe we could discuss in a coffee break later. I've done a bit with matching origin and destination, and maybe some of the data could be reused for that.
Yeah.
Good. Next question.
Hi, thank you so much for your presentation. Very interesting. Also very nice to see MRO at OpenSky, as you know. My question is regarding the transferability to a hybrid electric system, because weight will be probably handled very differently if we're flying hybrid electric. Plus, weight in general is a problem in aviation, but especially in electric flying. And how, so we might see weights that we have not seen so far, and the weight will definitely have a much different impact. How do you plan on handling this, or how do you model this, or do you just assume current weight, or do you have some estimations?
It's true. It's a great impact, the weight penalty. For now, we focus on the A320 in a scope like the airframe will not change, the trajectory rules will not change. It's only isolated the propulsion system. But yes, the weight influence is there. What we were very happy about, that by considering the hybrid electric or the electric components in the hybrid electric system with an degree of hybridization of like 2 to 3 megawatts, we did not exceed the maximum takeoff weight of the aircraft, which made us very happy.
Okay, thanks. So you do not have like a model for what weight is to be expected on an A320, because I believe Airbus is developing like systems for A320 in like hydrogen and also hybrid electric, but you do not have any data there, right?
I don't have it here, but we estimated it. And yes, it changes with degree of hybridization, and we will model it in the general scope. It will be definitely a factor which we will consider.
Okay. Thank you so much. Looking forward to that.
Yeah. I agree. It would be really interesting to see the follow-up research on that. More questions?
Hello, thank you for this presentation. You have been able to devise the thrust thanks to the flight parameters and weather information, meteorological data. My question, do you think it is possible to go further and, for example, to try to extrapolate which could be the turbine internal temperature, for example, that could affect the MRO depending on the thrust you have computed?
Yes, this is definitely where my research will go. When we see the right graph, I think this is what you know, what you mean, the thermal loads, turbine inlet temperature.
Exactly.
Yes, it's one of the main key parameters for maintenance correlation. So yes, this is why I show the graph, because of the importance of that. And later on in the degradation model, yes, there will be, this will be considered. So this is, I stopped here at the thrust profile, but the key aspects we do at our institute, it's the engine performance calculation. So to have the ambient conditions, to get the operating point of the engine, and to calculate the turbine inlet temperature, for example. So yeah, we will do that.
Do we have more questions? We still have a bit of a time. No more question. I have a very brief one. Maybe what is the timeline for this kind of research? What do you think when these things will actually be implemented, and what is the plan, at least?
When the project was started, it was said to be in the scope more of 2033, 35, more in that than in 2050. So
yeah,
more
good to hear. Yeah, nice.
So more the midterm time frame, which is why we also consider the A320. We consider the engine V2500, where we have the current engine models. So we say much stays in the scope of today, but is in near future hybridized.
Futuristic.
Yes, and not too futuristic. But if it's true, we will see, because new engine concepts, new airframes, they take a long time and are operated over a long time. We will see how it will be in real life.
Nice, thanks. Have more?
Maybe I missed that, but how do you guesstimate, or how do you know the takeoff weight?
The takeoff weight is correlated from flight distance, great circle distance.
Okay, if you don't have more comments. Okay, we have
There
Zoom.
is somebody online with a question.
Who is responsible for the online? Should we try to check? Okay, so just unmute yourself and you're okay to speak?
Yeah. So when the plane takes off, you have a moment when you go from takeoff thrust to climb thrust. And that moment is quite controversial, because sometimes it's specified at a low height and sometimes it's specified at higher heights. It's for people uncertain at what height they actually do that conversion from takeoff to climb thrust. Now, is this something that you could find back in your analysis? So the exact moment of transfer.
We did not look into it in that detail in order to really find this point, but I believe that it is in the trajectory, as we have the kinematic trajectory, and then at the kinetic aspects, the weight, and then that we see it when we do the flight mechanics to extract the thrust in order to fly such a trajectory at this takeoff weight. If it answers the question.
Okay, yeah. I hope it does.
Yeah, let's hope it. Let's see in future if we really can detect this height, because it's always something that's hidden by the operators of the airline, so they don't want to tell us. So we are really looking for a way of discovering at what height they really go from the one thrust into the next thrust, because it had such a big impact on the sound.
Thank you very much for that information.
My pleasure.
Okay. Thank you all.